All right, let's talk about an AI that's doing something completely different. It's called GILT. And believe me, it's not just another chatbot. This thing is set to totally change how AI sees the world, specifically how it understands the connections between, well, everything.
So you've seen AI write poems, you've seen it paint incredible pictures. That's amazing, right? But what about understanding something like this? This is where things get really tricky. We're talking about a challenge that goes way beyond just words or pixels. And that challenge, that puzzle, it all comes down to something called graph data. Now, I know, it sounds a little technical, but stick with me, because this stuff is literally everywhere. It's like the secret blueprint mapping out our world.
So what is it? Really, it's just about connections, relationships. You know, your social network? That's a graph. It's just mapping out who's friends with whom. A complex molecule? Yep, that's a graph too, showing how all the atoms are linked up. Logistics networks, citation networks, all of them, at their core, are just graphs.
Okay, so here's where we hit the big wall. The core challenge has this fancy name, graph heterogeneity. But all that means is that every single graph is totally different. See, text and images have a universal language, right? Words and pixels, but with graphs, every single one can have its own unique structure, its own features, its own rules. Each one is a unique snowflake, and that's an absolute nightmare if you're trying to build one AI that can understand them all.
Take a social network, for instance. Its language is all about user profiles, who's friends with who, what you like. But then you jump over to a biological graph, and suddenly you're talking a totally different language. It's all about the cold, hard numbers, atomic properties, that kind of thing. And then a logistics graph? That's all about maps, right? Geographic coordinates? So you've got three completely different worlds, each speaking its own unique language. So, you're probably wondering, how have we been trying to tackle this? Well, the AI playbook so far has really had two main approaches. And, spoiler alert, they're both kind of flawed. Okay, so approach number one is the LLM method. The idea is to basically translate the graph into words and just feed it to a large language model. The fatal flaw here? It's text only. It's like trying to describe a molecule's structure using a sonnet. You lose all the numbers, the science, the stuff that actually matters. Then you've got approach number two, the tuning method. Here, you take a general model and then you painstakingly retrain it for every single new graph. Think of it like this. You have a master detective, but for every new case, you send them back to the academy for 4 years. It's just painfully slow, a huge bottleneck. And this is where things get really interesting. This is where GILT comes in. GILT doesn't just play by the old rules. It throws the whole rulebook out and starts a brand new game.
I mean, listen to how the creators put it. They say they've built GILT as a framework that is, and I quote, LLM-free and tuning-free. That's the whole magic right there. It's designed specifically to avoid those two big traps we just talked about.
So how does it do it? What's the secret sauce? Well, it's a brilliant two-step move. First, GILT acts like a universal translator. It has this process called graph native tokenization, which basically takes any graph's unique, weird language and turns it into a standard set of tokens, a language everyone can understand. Then, step two, it becomes this amazing quick study detective. It has what's called an in-context reasoning transformer that can just look at a few examples from a new graph and bam, it learns the rules on the fly. No retraining needed. It just gets it. Okay, that all sounds great in theory, but does it actually work? Well, let's take a look at GILT's winning score, because honestly, the results are kind of mind-blowing. Let's start with accuracy. We're looking at a really tough task here, classifying nodes in a graph with just a few examples to learn from. And look at that, GILT is right at the top. It's not just beating the competition, it's leaving the LLM-based approach in the dust and inching out the other top contenders. And it's not just a one-trick pony. Not at all. It's also fantastic at something called link prediction, basically figuring out missing connections in a network. And it even achieves state-of-the-art results in classifying entire graphs, like really complex molecules. This thing is a true generalist. But honestly, for me, this is the real kicker. This is the difference that matters most. Speed. Look at this. The tuning-based models take about 30 seconds to solve a task. The LLM-based models, we're talking around 10 minutes. And GILT, it's done in less than a second. Less than 1 second. I mean, just think about that. We're not talking about it being a little bit faster.
We're talking orders of magnitude faster, up to 1,000 times faster, and sometimes even more. That's what makes this thing practical. That's what makes it scalable for real-world problems.
So what's the big takeaway here? It's actually pretty profound. GILT is doing something fundamentally different. It's not translating everything into human language and then trying to reason about it. It's performing what you could call graph-native reasoning. It's figuring out the rules of the game directly from the numbers and the structure of the network itself. It's not just parroting human knowledge, it's actually inferring the logic of the system on its own.
And that leaves us with a really exciting question to think about, right? If we now have an AI that can learn the unique language of any network instantly, what does that mean? What hidden connections in science, in medicine, in technology are we about to uncover? What problems that seemed impossible before are suddenly within our reach? It's an incredible thought. Thanks for diving into this with me.